Alright, here's a quick problem. Suppose we have two normal subgroups n1 and n2 of G, and suppose the commutator of G and n1, so that's all things of the form G and G inverse n inverse, where G is in G and n is in n. Well, not all things of that form, but the subgroup generated by all things of that form. So this is contained in n2, which is contained in n1. And let H be any subgroup of G. Now prove that N2 times H is normal in N1 times H. Do I say anything about how these are in fact subgroups? I don't think I mentioned it anywhere, but it's sort of obvious because N1 and N2 are normal, and so by one of the isomorphism theorems. Is it the second one or the third one? I don't know how they're labeled. But one of the isomorphism theorems tells us that if you just take the product of a normal subgroup and a subgroup, you get a subgroup. And so this is, of course, is saying not only is it a subgroup, but it's a normal subgroup. But it's normal in N1H. So anyways, let's take some N1H1 in N1H and N2H2 in N2H, these guys. Then conjugate N2H2 by N1H1, and then you get this thing. And then, let's see here, what do we do here? H1, N2... So we've basically just taken, all we've done is we've taken this element and multiplied by h1, n1. So there's sort of a break here. Everything to the left of this line that I just drew is literally what we just had before, and everything to the right is just something times its own inverse. And so this thing to the right, you're just multiplying what we had by the identity, and so it's the same. But now if we look at, I've sort of written this in a suggestive way where I've got this n1 and then this whole thing in parentheses and n1 inverse and then this other thing in parentheses inverse. And so that looks like an element of a commutator subgroup. And then, of course, this thing on the right here, we also can further expand that by throwing this h1 inverse h1 in here, which, of course, we can do because that's the identity. Now we take our element G to be this thing in parentheses above here. So once we have that, certainly this is going to be some element of G. But furthermore, let's see here. We have n1 is in n by definition. In fact, it's in n1, and n is not defined here. So that is a typo. This should be n1. So n1 is in capital N1. And obviously G is in G, capital G. So then N1, G, N1 inverse, G1 inverse, this is in the commutator of G and N1. And of course, G, the commutator of G with N1 is equal to the commutator of N1 and G. That should be clear by the definition. And then by assumption, this is contained in N2. So this whole thing is contained in N2. So what we have so far is this whole thing right here is contained in N2. Okay, so that's good. For normality, we're going to want this entire thing on the right here to be contained in N2H. So this is in N2. That's good. We're on the right track. For the other stuff we've got N2 is normal in G. So let's take H1, N2, H1 inverse. By normality, this is in N2. And certainly if you take three things in H, that's going to be in H. And so then, let's see here. Okay, so this is going to be in N2, and this is going to be in H. Okay, so looks, and then you're multiplying these two things together, and so this whole thing is going to be in N2. And so that means that what we started with, this N1H1, N2H2, N1H2 inverse, is an element of N2H. because all this junk here is an N2 and all this stuff on the end is an H. But that's exactly what you need to prove normality, and hence N2H is normal in N1H. And that's exactly what we wanted to prove, and so we finished the proof.